This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll go over boiling point and colligative properties. Boiling point is the temperature at which a liquid becomes a gas. And remember that as you heat up a liquid, the molecules in that liquid are moving around faster and faster and faster. And once they have enough energy to escape the liquid and leave that liquid surface, then that molecule is now a gas. And a lot of the things they have to overcome are intermolecular forces. Intermolecular forces were covered way more in depth in lesson 8 that talks about covalent compounds, so go back and watch that if you're not familiar with them, because we're going to be talking about them a lot right now. These 5 images are in order of highest boiling point to lowest boiling point, and they all show us something different that contributes to the boiling point of a substance. The first one is hydrogen bonding. Hydrogen bonds will result in the highest boiling point because those are really strong intermolecular interactions, so your molecules need a lot of energy to overcome those interactions and become a gas. The next one is dipole-dipole interactions. So these will contribute to the second highest boiling points because these are also fairly strong intermolecular interactions. The last 3 molecules here, 3, 4, and 5, are all nonpolar molecules. And nonpolar molecules don't have the dipole interactions like we saw with 1 and 2 with the partial negative and partial positive charges. And the only intermolecular interactions between these are London dispersion forces, which is also covered in way more depth in lesson 8. When we compare 3 and 4, we want to notice how they kind of look like puzzle pieces in that they can stack on top of each other and fit together really nicely. And that increases the amount of contact area that they have between the molecules, which increases the opportunity for London dispersion forces. So there are more London dispersion forces, the more contact area we can have. Now compare 3 and 4 to image 5. Image 5 has this branch on this hydrocarbon. The branch interferes with the stacking, so they're unable to have all of that contact area that we see in 3 and 4, which that will drastically reduce the boiling point. The difference between 3 and 4 is that they are different molecular weights. Because if we look at the structure, they both stack, so they both do a really good job of having maximum contact area. But number 3 is heavier than number 4. So the molecule number 3 has that extra carbon. And what that does is it means that we now need more force. Because it's a heavier molecule, we need more force to make it a gas now. So I'm going to put a list on here that shows what is most important when considering boiling point. So the intermolecular interactions are far more important than the molecular weight, and then the dipole and H bonds are way more important than the amount of London dispersion forces. The last thing you want to consider when thinking about boiling point is air pressure. So here we have this container that has air, and we have P air to represent the air pressure, and then we have a liquid in this container. The air pressure points down, shown by these arrows. So the air pressure is pushing down on the liquid, which is making it harder for those liquid molecules to escape as gas particles. So the more air pressure you have, the more downward force you have, which means you're going to need a higher boiling point, or you're going to need a hotter temperature in order to turn those liquid molecules into gas molecules. Next, we're going to look at colligative properties, but before that, we need to look at these units of concentrations. The first one is molarity, which is moles of your substance X divided by liters of your solvent, which is usually water. It's represented by a capital M. And anytime that you see a substance or element surrounded by brackets, that's referring to its molarity. We'll cover molarity way more once we get into solutions, but that's all you need to know for now. Molality is the moles of X, just like before, but instead of liters, we divide it by the kilograms of your solvent. And it is represented by the lowercase m. The last one is osmolarity. In osmolarity, we start with the exact same approach as molarity. So this is big M for molarity. And then we multiply that by the number of solute particles per molecule. So the term on the right. And what this means, we can explain by looking at these 3 molecules on the right. If you take a molecule of sodium chloride and put that into water, it will dissolve into 1 sodium particle and 1 chloride particle. So it dissolves into 2 particles. So we would take the molarity of sodium chloride, let's say it was 5 molar of sodium chloride, multiply it by 2, because that would be 2 particles per molecule, to give us an osmolarity of 10. If we did this with glucose, so if you put, let's say, a sugar cube into water the glucose molecules themselves do not dissolve into multiple particles. So every glucose molecule stays completely put together. So there's only one solute particle per glucose molecule. Compare that to the next molecule of sodium sulfate. All the molecules of Na2SO4, when you put them into water, would dissolve into two separate sodium particles, and then one sulfate particle. So that would be 3 particles per molecule of sodium sulfate. Now that we got our units of concentration down, we can talk about colligative properties. And colligative properties are changes in the physical properties of a liquid once you add a solute. The first one we'll look at is boiling point elevation. To conceptually understand boiling point elevation, think about whenever you add something like sodium chloride to your water and how the positive sodium and the negative chloride are going to be able to interact really strongly with your polar water molecules. And that's going to make it harder for those water molecules to leave the liquid. So you're going to actually need a higher temperature in order to make that water boil. So that's why the boiling point is elevated upon adding a solute. The equation is really straightforward. We have delta T, which is how much our boiling point was elevated, times I, which is the number of solute particles per molecule, which we just discussed for osmolarity, times Kb, which is a constant that depends on the solute and the solvent, and then times the molality, which we discussed above. The next one is freezing point depression, which has a super similar equation to boiling point elevation. You just use Kf instead of Kb, and Kf is also dependent on what solute and solvent you are using. And conceptually, the way you want to think about this is that solids have pretty organized lattice structures, and when you add a solute, you're disrupting that lattice structure, so you're going to need to get even colder in order to reform that lattice structure. The last thing we'll go over is osmotic pressure. And to explain the concept, look at this image on the right here. And this image is a container that it holds salt water, and then inside the salt water there's a bag of pure water. So this bag, represented by the red, is holding pure water. And what happens is if this bag is permeable to water, so water can move in and out, the water will travel from the more pure area to the area with more solutes. So over time, that bag of water is actually going to shrivel up because the water has left the bag. And you can see this with cells. If you place a cell in really salty water, then the water will leave the cell into the salt water. And then if you take a cell and put it in pure water, now the cell has more solutes than the pure water. So then the water will move into the cell, and that cell is going to grow, and it could even burst if it takes in too much water. The movement of the water creates a pressure, which is represented by this pi symbol, and that is called osmotic pressure. It equals a really straightforward equation, so it equals I, which we've already talked about, the number of solute particles per molecule, times molarity, which we talked about above, times R, which is a constant here. They are probably going to give you this constant if this ever comes up on the test, and then you multiply all that by whatever temperature it is that you're working with. Osmotic pressure will come up again and again in biology topics, so it's something you want to make sure you really understand. The last thing we're going to look at is vapor pressure. To understand vapor pressure, look at this image on the far left. And this is a container that has liquid water, and then it's sealed off on the top. So at all times, some liquid particles are going to become gas particles, even if it's not at its boiling point. And that is because just due to the random motion of particles, sometimes a liquid particle is going to get enough kinetic energy to overcome all those forces and then become a gas particle. So we will have some liquid becoming gas. And if we put a lid on top of this container, then over time, we're going to start getting a collection of water vapor above the liquid. And that's going to create a pressure for that water vapor, which is represented by that term pH2O. Over time, as we get more gas particles, then we're also going to notice that some of the gas particles are turning back into liquid because they're losing kinetic energy and they turn back into a liquid. And eventually, the rate of gas to liquid is going to equal the rate of liquid to gas. And then once they're equal, the amount of liquid is going to be constant and the amount of gas is going to be constant because those rates are equal. When those rates are constant, that's called dynamic equilibrium. And then the vapor above has a pressure, and whatever vapor pressure that is, that leads to dynamic equilibrium, that is the vapor pressure. Now let's look what happens to vapor pressure whenever we add solutes. So this middle image is basically what we talked about on the left. So equilibrium has been established, and then we added solutes. When we add solutes, just like what we said earlier in the video, it now makes it harder for the liquid to become a gas. So your rate of liquid to gas has gone down. So that's what's represented by that shorter arrow. But the rate of gas to liquid is unaffected. So now we have more gas turning into liquid than we have liquid turning into gas, which means the vapor pressure is gradually decreasing because we have less gas particles over time. And that means the rate of gas to liquid is also decreasing over time because we have less gas particles. So gradually, the rate of gas to liquid is going to lower until these two rates are equal. So in other words, the equilibrium gets reestablished after we add the solutes. And once that equilibrium is established, ask yourself, what's the pressure of my H2O, of my water vapor? And we said that the water vapor pressure is going to go down because more gas became liquids. So by adding solutes, the vapor pressure goes down. Now let's look at what happens to vapor pressure when you increase the temperature. So we've established equilibrium. So we're starting from basically what we talked about in the first image. Equilibrium has been established, and then we turn up the temperature. So ask yourself what happens to the rate of those two things. When you increase the temperature, you have more liquid turning to gas. So what happens is over time, you have more gas particles, so your pressure of the H2O is going up. And as you have more gas particles building up, your gas to liquid rate is gradually increasing. And then eventually, equilibrium will be reestablished. And then the pressure that you have once equilibrium is reestablished is your vapor pressure. So increasing the temperature increases the vapor pressure. And real quick, going back to the part about solutes, we concluded that vapor pressure was lowered. And at the same time, you could also say boiling point was risen by adding the solutes. So anytime that your vapor pressure goes down because you did something like add solutes, your boiling point would increase. So that's just a connection you want to make sure that, for one, makes sense and that you know that that is the correlation between those two. The last thing I want to do is give you a different way to think about this that may be a little bit easier and you can apply it a little bit more quickly. I would definitely try to get what we talked about before understood because that's the more technically sound way to go about it. But you can also think about vapor pressure as, if you look at this image on the bottom, it's the upward force created by the movement of the water molecules. And if that upward force gets strong enough, then those molecules can become gas molecules. So think about the two situations we discussed when you add a solute and increase temperature. So when we add a solute, we're making it harder for those liquids to move around because they're more stuck together. So we lowered that force, that upward force. So whenever you add a solute, it's a little easier to see that we've lowered vapor pressure because there's less upward force. Conversely, when you increase the temperature, the molecules are bouncing around more, so they're making more upward force, and they're more likely to become gas particles, which that corresponds exactly what we said before, how the vapor pressure increases. So you should end up with the exact same conclusion about vapor pressure, and it's a little bit easier way to think about it. However, what we talked before is definitely something that's good practice to try to make yourself think through.